In this lecture, we are going to look at the networking issues in IoT. In the previous lectures, we looked at the connectivity issues, that means with respect to communication, what are the challenges that are there, what are the solutions that are available, the IEEE 802.15.4 standard and the different protocols which follow those standards. We looked at in significant detail. In this particular lecture, we will sort of conceptually continue with whatever we were discussing, but from a networking point of view, we will look at the different other aspects of setting up IoT systems, and from a network point of view, what are the solutions again that are there in order to address. So, let us first look at some of the characteristics of IoT devices, but before that let us quickly recap the typical network that is encountered in IoT systems. So, the typical network that is encountered is that we have a source, a data source or multiple data sources consisting of sensors, typically sensors, RFIDs and so on, which collect, which interact with the physical environment, collect the data, and then the data is sent elsewhere for further processing typically, and then based on the processing, based on what is determined by the data, that is analyzed. So, some system would be actuated, it may or may not be actuated, some system may be actuated or there may not be any actuation associated with the system at all. So, we have seen both of these types in the previous lectures. So, let us, with this kind of backdrop, let us try to understand that what are the challenges ahead if we need to build up this kind of system. From the connectivity point of view, we have already seen, but from a network point of view, how to set up the network, let us try to understand this. So, going back, these are the characteristics of IoT devices. The IoT devices typically would consist of different sensors, etc., typically, but not necessarily. So, irrespective of what they contain, these IoT devices will have very low processing power. They are very small in size and they have energy constraints because they are typically battery operated, and because of the small size because of their small size, the batteries that are used are also small, and due to the electrochemical limitation of the batteries. So, what happens is these batteries will have a very limited lifetime. So, what you need to have is to have solutions at the hardware and the software and the algorithmic level, which will consume very low power. So, from a network point of view specifically, we need systems, we need protocols, we need solutions, we need algorithms which will be consuming extremely low energy. So, we have in each of these IoT devices in the network, in the IoT network, which are energy constrained, they are small in size and have very limited processing power. So, network protocols that are designed for use in IoT should be designed accordingly, keeping these constraints in mind. So, from a network, that is from the device point of view. From a network point of view, these networks typically support very low throughput, they have high packet loss, they have very high packet loss because these networks typically operate in environments which are very much noisy, there are a lot of interferences, consequently the packet loss is also high, and they have tiny useful payload size, and in most cases these networks also exhibit the behavior of frequent changes in their topology. So, as you can understand, it is a highly constrained dynamic kind of scenario, and coming up with networking solutions is a huge challenge in these systems. So, classical internet, that the one that is based on TCP/IP, the classical internet that we all use is not meant for these constrained IoT devices. So, from a holistic viewpoint, the challenges can be classified into different types. We have challenges with respect to access, there is heterogeneous access, heterogeneous traffic flowing through these networks, there is heterogeneity in the devices, in the vendors, in the specifications, in the standards, in the protocols that are used by these devices and the devices working in these networks. And as I said before, the devices are constrained in all respects: energy, processing, communication and so on. So, in all respects these are constrained. So, you have heterogeneous access, heterogeneous traffic flowing through these networks and heterogeneous devices and constrained devices. All of these holistically from a network point of view make the designing of these systems very challenging. To think about IoT, let us think about a tree. So, this analogy has been taken from the source that is given on the slide. So, let us think about the tree. In a tree we have the roots, in a tree we have the trunk of the tree and then we have leaves. So, the different IoT applications like smart healthcare, smart transportation, smart cities, smart energy, smart retail, smart home, smart cities overall, all these smart things that we talk about in the context of IoT, these smart applications, they are analogous to the leaves of a tree. At the very bottom of the tree are these roots. These roots are like communication protocols and device technologies, communication device technologies. So, these protocols and device technologies are sort of like the roots of the tree. Technologies such as Bluetooth, Zigbee, Z-Wave, wireless HART, Wi-Fi, sensors, actuators, these are the different roots of the tree. So, considering the IoT applications on the very top and the roots like the ones, the technologies, the protocols that I just mentioned, the objective is to come up with a suitable trunk that will support these applications and will connect with the roots of the tree. So, this trunk is basically the architectural reference model of IoT, the ARM model of IoT. So, overall from a optimization kind of viewpoint, the goal can be stated like this, that we need to select a minimum set of roots and propose a potential trunk that enables the creation of maximum set of leaves. So, this can be thought of like the overall objective, the optimization objective in this particular context. Now, think about IoT. IoT we can think about offering non IP based proprietary means like vendor specific solutions, or we can think of using the IP based solutions based on the IETF protocols that are already there. So, we can have the classical internet that everybody uses be adopted for supporting IoT networks. So, we have proprietary non IP based solutions and these use vendor specific gateways, vendor specific solutions of all kinds including the APIs. On the contrary, we have IETF IP based solutions where there are different initiatives to support IoT like the 6LoWPAN, which talks about IPv6 over LoWPAN, which is low power wireless personal area network, and this is the one that we discussed in the context of connectivity in the previous lecture. So, IPv6 over 6LoWPAN is one such technology, one such protocol which is being worked upon by a specific 6LoWPAN working group. Likewise, there are other working groups talking about the adaptation of IoT requirements to the internet. So, that you can use the existing internet to support IoT applications. So, among these are role. Role is basically routing over low power lossy networks role, and then you have the core, which is constrained restful environments. 3 different working groups are there. Like this, there are multiple different initiatives in order to have support of IoT over IP, that means the existing internet. That means we are talking about coming up with solutions of adaptation for use of IoT in existing IP based systems, IP based networks. So, going back, we have proprietary non IP based solutions. So, for example, we could be talking about the use of different sensor networks. So, where different sensor networks, different sensor systems could be using proprietary solutions, proprietary protocol stack, right. So, this is this part, and then we have on the other side you have different devices such as laptops, desktops, then these PDAs and many others, which typically in the existing framework use the existing TCP/IP protocol stack of the internet. So, now what we need to do? We need to come up with a solution which can fit these proprietary solutions to the existing framework of the internet, which is already supporting laptops, PDAs and different other wireless devices. So, this is this holistic framework that we are talking about over here. But the drawback of these non IP based solutions are that there is limited flexibility to end users, and so because these are vendor specific APIs, there is limited flexibility that the end users have. In terms of interoperability, there are vendor specific sensors, vendor specific gateways. Each of these speak different languages. It is somewhat like some sensor nodes, some IoT devices speak one specific vendor specific language. Let us say that somebody speaks analogously, that somebody speaks English, somebody speaks French, somebody speaks Hindi. How they can talk to each other? There is no common language, there is no interoperability between them. So, you need to in order to conquer this kind of heterogeneity, you need to have a common framework which will make these disparate devices following different proprietary standards talk to each other. So, interoperability is this issue which talks about conquering this challenge of heterogeneity in all different respects. The last one is that limited last mile connectivity. Most of these non IP based solutions offer limited last mile connectivity, because these are not models which are supposed to scale up, unlike the IP ones, which IP has been designed in such a way so that the scalability can be maintained. That means that IP is a scalable solution, unlike these proprietary vendor specific solutions which are not non-scalable, but limitedly scalable. So, we have different IP based solutions as well, typically following different initiatives by IETF. 6LoWPAN, role and core are 3 different important ones which I mentioned already. IPv6 talks about how you can do header compression, encapsulation, how you can harness these in order to allow the IPv6 packets from the network layer to be transmitted over IEEE 802.15.4 based networks, and this we have seen in considerable detail in the previous lecture. Role is about how you can optimize the routing protocol etc. for saving on storage and energy. So, role is a new kind of routing protocol that can be used for IoT based applications, and core, constrained restful environment, extends the integration of IoT devices from networks to the service level, and this is what is very essential. It is a important thing, service level. Typically we talk about the networks, we talk about collecting data from these networks. In the context of IoT, it is even more significant. So, here we are talking about services. IoT is mostly, if not completely, about offering different services. So, this service consideration in core is very crucial and is of is an attraction in the IoT community. So, before we get into the further details of core, I would like to talk about a very fundamental concept, so that we ensure that we really understand what we are talking about. So, let us say that if we consider an IoT network, this is how it is going to look like. So, we have different IoT devices which are the things, and these things could be sensor enabled, sensor based. Let us say that these are IoT based, right. So, IoT based things, sensor enabled. These data that are collected from the things which are fitted with different sensors, these will then transmit that collected data through something like a local area network, then send that data further through the internet to the back end. And this back end would have all kinds of processors like servers, then you will have storage devices, including cloud, etc., in the present context. In the modern context, we talk a lot about using cloud based services for processing, storage, etc. So, that back end could be cloud based. So, this is this network and the corresponding protocols, architecture and other aspects of solutions that we need to understand in considerable detail. So, here in this lecture we are simply introducing you about the overall concept of the networking aspects, but gradually down the lane throughout the course we will talk about many of these things in further more detail and their applications in the real context. So, we were talking about core, right. So, we saw that there are different IETF initiatives on supporting IoT over existing internet, and let us talk about the core, which is the full form of which is constrained restful environments, constrained restful environment. So, as you can see over here, REST, rest is an acronym, So, we are talking about the architecture which supports REST, and we need to see how that helps in building up core. So, core basically provides a platform for applications meant for constrained IoT devices, and that is what this constraint part is important, and that is where this use of core for IoT comes into picture, and that is where this finds itself useful for IoT environments. So, this framework views sensors and actuator resources as web resources. The framework is limited to applications which monitor basic sensors and supervise the actuators. So, COAP includes a mechanism for service discovery, and it is this service discovery that makes it very interesting. So, let us look at the service discovery aspect of core. Core devices are like mini web servers that register their resources to the resource directory and the registration interface. So, a resource directory is a logical network node that stores the information about a specific set of IoT devices. So, it is basically about storage, a logical IoT node storing the information about a set of IoT devices. The registration interface, on the other hand, supports the REST based protocol, the REST architecture, the full form of which is Representational State Transfer architecture, which would support protocols such as HTTP for the existing internet, and for IoT the equivalent of it, which is the COAP, which again we will talk about in a little bit further detail in a short while. So, IoT client uses the Lookup interface for discovery of IoT devices. Now, everything is fine, network has been built, but then whether the network is able to offer the quality of service guarantees or at least some acceptable levels of quality of service. And that is what is also very important, because IoT networks are all centered on services. So, let us try to understand what are these quality of service issues. So, quality of service of IoT network talks about guarantees with respect to offering different services to the IoT applications through controlling the heterogeneous traffic generated by IoT devices. QoS policies for IoT networks include resource utilization, data timeliness, data availability and data delivery. These are the 4 different attributes which are of prime consideration in the context of QoS and using and ensuring QoS for IoT networks. So, let us look at each of these 4 things in further detail. Resource utilization is the first among the 4. It talks about the concept, the requirement of the concept of control on the storage, and bandwidth for data reception and transmission. We are talking about resources. Resources in the context of networks mean different things such as storage, bandwidth, etc. The control over these resources such as storage, bandwidth, etc. for reception and transmission is something that has to be considered as a QoS criterion, and this is quite fundamental. QoS policies for resource utilization include resource limit policy, which controls the amount of message buffering, and this is useful for memory constrained IoT devices. And the second one, the QoS policy for resource utilization, is time filter policy, which controls the data sampling rate, and this basically talks about the inter arrival time to avoid buffer overflow. So, this talks about control over the network bandwidth, memory and processing power. Timeliness, the second attribute, is basically the measurement of the freshness of a particular information when it is received at the receiver end. So, from the source till the receiver, the data that is sent at the receiver, it is received, but then when it is received at the receiver, how much fresh that data is, and this is a very important consideration, particularly for applications where safety criticality, where there is real time requirements are there. For example, healthcare, the patient having heart attack, for example, it is a very important QoS criterion to measure whether the data that is received at the receiver end, maybe somebody having a heart attack, the packet containing that information, whether that is fresh enough, whether the data has been received timely or not. So, this is a very important consideration in many of these applications. Then data timeliness policies for IoT networks include the deadline policy. That means the maximum inter arrival time of data, how much is the maximum inter arrival time, and provisioning for it. This is a very important policy consideration. The second policy consideration is the latency budget policy consideration, which is the maximum time difference between the data transmission and reception from source end to the receiver end. So, so these are the 2 different considerations for data timeliness. The next attribute is the data availability, and availability, as this name suggests, it is the measurement of the amount of valid data provided by the sender or the producer to the receiver or the consumer. QoS policies for data availability in IoT networks include durability policy, lifespan policy and history policy. Durability, as this English term suggests, it talks about the control of the degree of data persistence transmitted by the sender. So, data persistence is important, that means ensuring the availability of the data to the receiver even after the sender is unavailable. So, the persistence of the data at the receiver is a very important durability policy consideration. Lifespan policy talks about the control over the duration for which the transmitted data will remain valid, how much the data that has been sensed and is being circulated through the network, how much time it is going to survive, how much time it is going to live. So, this is a lifespan policy. This is the lifespan policy. History policy is about controlling the number of previous data instances available to the data. So, in the history of the data, how many such instances are available to the receiver. So, data delivery is the last one. It measures, it is about the measurement of successful reception of reliable data from the sender to the receiver. QoS policies for data delivery are basically the reliability policy, which is about which talks about the control of the reliability level associated with the data distribution, and the transport priority, which allows transmission of data according to its priority level. So, with this we come to an end of the first part of IoT networks. We will continue with the different other aspects of networking in IoT, and before we talk about those things in detail, there are few other issues that also need to be considered, and that is what we are going to talk about in the next lecture. Thank you.